Double integrals. Double integrals. What does a double integral compute? So if I have this general double integral of the function f over the region D, what did we say that in general that computes? What does that compute? Gotta know this. What's that? Oh, people are saying net volume. Well, what's that? What's that? What's net volume? What does that mean? What is net volume? What is that about? Yeah?
It's like the total volume would be the xy plane in your surface.
Okay.
Because it can dip below, which would be the negative volume, so it's like the total.
So net volume is total volume?
Or it's like the.
It sounded like you were going to add up all the volumes above and below. Is that right?
Yes.
No.
No.
But you're right. You're on the right track. It has to do with the fact that there's some of these. If f is carving out solids below the xy plane, you're going to have more than one volume going on there. Yeah. Yeah.
Oh, yeah.
Yeah.
That's
Right.
what I was-
Yeah. But so total volume is different. Total would mean you're adding up and getting all the volume. So anytime you get a solid below, those volumes get subtracted out. That's what the double integral does. Because f would be negative, right? So when f is negative, whenever f is negative, those points of D are going to have a negative contribution to the overall double integral. So you're going to get a difference of volumes. All the ones above minus all the ones that end up below the xy plane. Okay, so another term for that is signed volume. Okay, so the signed volume of the, so there's lots of details here though. The solid formed between f and the xy plane within the vertical cylinder defined by D's boundary, right? So the boundary of D gives us like the lateral sides of this, and then the top or the bottom is the function f, and then also the top or bottom is the xy plane, depending on where f is, okay? So signed volume is another way to say net volume or difference of volumes. Okay, so that being said, suppose f is a positive constant function, right? So suppose fxy is just z equals k. Then what would the double integral find? What would it compute? So it would still be signed volume, but we can say something more specific now. What's that? Just volume. Volume, so more specific than that. So now we know z equals k. K is positive. So what would the double integral find? We got lots to do today, so if you think you know the answer, shout it out. Edis, what would?
I mean, I think it's just the volume under the surface.
Okay.
There's something more specific, I think.
All right. So then that's a right cylinder now, right? Because it's you have the same cross section all the way up, all the way to the top. So you get the volume of this right cylinder. Right? We talked about cylinders, right? Cylinders. So this is a solid cylinder. Okay, and so that's the same as the area of the base times the height. What's the area of the base? The area of the base is what? The area of D, and what's the height? Okay, right? So really, if your function was a constant function z equals k, then the double integral would find the volume of this right cylinder, which would be the area of D times k. Are we good? Does that make sense? Okay, so then how could that double integral then be the area of D? If k equals 1, right? So if k equaled 1, then the value of that double integral would be that volume with height 1, but that would be the same value as the area of D. Does it make sense? So if k equals 1. In other words, if k equals 1, what are we saying about f, the function f? Well, it was flat this whole time. We're saying constant k, but more than that.
Z equals 1?
Yeah, so the function then is the constant function 1. z equals 1, or the function f of xy equals 1. So then what does the double integral become?
The area.
Oh, so the symbols of the double integral. If f of xy is 1, then? Yeah, just the integral of 1 times dA. So in that case, then if the function is just the function 1, and you compute the double integral, the value of that is going to be the area of D by this train of logic. So what are we doing? It's like we're tricking the double integral, which usually finds signed volume for us. By forcing f to be 1, we trick that signed volume to have the same value as the area of D. Do you see it? Does that make sense? But double integrals, they still find signed volume. They still find net volume. It's just this, by making the function be the function 1, then that value of that volume has the same value as the area of the region in the xy plane. Yes, please.
So it's just like a degenerate volume then? Special case?
No, so it's still finding this volume that I'm showing you here with height 1. But that value is the same as the area of D. So it's still, the unit is still a volume unit. But that number, the number has the same value as the area of D. Okay, so keep that in mind. So this is a way that you can use double integrals to find areas. We kind of trick it, right? If the function is 1. Okay, moving on. So let's go back and look at this one. This is the last one we did last time. And if you remember, we figured out that this was 1/2 y was this line right here. Like this. And this is x equals 1/2 y, which is y equals 2x. And then this x equals square root of 25 minus y squared was, remember we found that was a circle? And what circle is that? That's x squared plus y squared equals 25. So radius is 5. And this was, what is this, type 1 or type 2? Type 2, left to right, right? Left to right, and then take all those from bottom to top, right? So left to right, bottom to top, right? Is our mantra for a type 2. And then we changed it into type 1, and remember changing into type 1 meant what for us when we changed that into a type 1 double integral? Remember what happened? Breaks into 2 because of what? Yep, the top, right? So our type 1 is bottom to top and then left to right. So the bottom is all the same, but the top is split into two different curves. Do you see that? The top is y equals 2x here, but then the circle on this side. So that's why we needed for type 1, we need to split that up, and we already did that. Okay. So now we're going to talk about a third way to approach this. There's still a third way to set this up as a double integral. Something different than type 1 or type 2. Anyone see what that might have to do with? Back from Calc 2, you learned something in Calc 2 that relates to this. Yeah, Ryan. Okay, so this is based on a circle, right? This region has a circular boundary. And so, circles centered at the origin are very friendly in polar coordinates, right? So polar coordinates. So let's talk about polar coordinates. What are our variables in polar coordinates? Let's do a crash course review. What were our two variables in polar coordinates? R and theta, good. So R is defined as radius, distance from, so the origin is now called the pole, right? If you're looking down on the top of the world, right? At the North Pole, okay? So distance from the pole is R. Distance out away from the center. And the other variable is theta, which is? It's our standard trig angle. What is that? That's the angle swept counterclockwise from x-axis, right? Angle swept counterclockwise from the x-axis. Okay, so looking at this circle, how is this circle related to r and theta? So the point, all the points on this circle, can you say about all the points on the circle there? In terms of distance from the pole or standard trig angle, does all those points on that circle have something in common? Isn't r always 5 for every angle, right? So this x squared plus y squared equals 25 is the same as r equals 5. Or r squared equals 25. So what's the relationship here between r and x and y? X squared plus y squared equals r squared. Right, that's our Pythagorean, so if we're looking here, this makes sense, right? Because if you have the x coordinate and the y coordinate, r is the distance out to that point. It has coordinates x and y. It's just the Pythagorean theorem, right? X squared plus y squared equals r squared. Okay, how do we so this is, if you have x and y and you want r, what about if you have r and theta and you want x or y? So remember, this is our angle theta, it's our standard trig angle. So what is x in terms of r and theta? This is all reviewed. This should ring a bell here, right? So r cosine theta will give you x, r sine theta will give you y. So those are relationships for polar coordinates as related to Cartesian coordinates. So we could say this region was defined by, y equals 0, x squared plus y squared equals 25, and y equals 2x. But what would it be now in terms of polar coordinates? This curve here would be r equals 5, right? And then what would this be in polar coordinates? Y equals 2x. So what are we saying? The y coordinate is always 2 times the x coordinate. So what would that boundary, that linear boundary be in polar coordinates? Okay, good. Who said that? Okay. The rest of you thinking that too? Okay, so this is a constant theta, right, for all values of r. And so that theta is the relationship of what? Rise over run, right? So, yeah, right. So there's the slope of this is 2, right? 2 for every 1. And so that means that that angle is what, arctan of 2, right? So it's like all points where r is between 0 and 5, and theta is between, what's theta down here at the x-axis? That's an easy one, right? So all points where the angle is between 0 and arctangent of 2, and all r values between 0 and 5. So you see that this is kind of well suited for polar coordinates. Okay, so what will our mantra be then? So our double integrals then in polar coordinates. So now f of xy is going to be, now x is r cosine theta, r sine theta. And then our our variables are r and theta. So our dA is going to have to do with r and theta. So is it going to be just dr d theta? So we want to explore that a little bit. But in general, what will our mantra be? Our mantra will be, so before it was like bottom to top, left to right, or left to right, bottom to top. So when we're talking about r and theta, what will it be now? So let me give you have a little, so we're talking about polar double integrals now. We're just taking this example and kind of, we haven't really established anything concrete yet, except we're kind of reviewing polar coordinates, and we're kind of just talking about this example a little bit. What would it be like with a polar double integral, right? So we know we got to change things x and y into r and theta. I mean, our dA is going to have to do with r and theta, like dr d theta or something like that. So let's take a look at an animation here and see how we're going to think about these double integrals. Any questions about just some of the basics here before I erase? Okay. Check this out here. So what am I showing here? So just watch and think about it. So here's kind of the first part. It'll go faster once it goes through once. I hope. There we go. Now it's too fast. So, what are you seeing? So here's part 1, part 2. Part 1, part 2. So talk to the person next to you. What is this showing about polar double integrals? Go. What is this showing about polar double integrals?
Yeah.
Slow again. Do manually. So part 1, part 2. So what is it showing then, in terms of double integrals? The way we're going to think about it is going to be what? First, let's see. Yes, sir.
Integrate for a given theta, all the radiuses within the region that you want.
Okay.
And then you do that for all of the thetas, and then you use the integral for all the theta.
Right. So we're gonna think about first for a fixed theta, integrating across R. So from like it's not going to be top to bottom or left to right, but like inside to out, right? Starting closest to the pole to away farthest from the pole. So like inside out, I guess is the best I can come up with. Closest to furthest from the pole. Closest to furthest from the pole for a given theta. And then we're going to integrate all those starting from starting theta to final theta. Now, so what I'm showing you there, though, is that those r's could be functions of theta, right? So f1 of theta, f2 of theta, not f. G, call it G. Now the question is it just simply dr d theta? Is that what dA is? So let's explore that a little bit. So our mantra, again, closest to furthest from the pole, starting theta to final theta. That's going to be our mantra for polar double integrals. Inside, or I said another way to say it for the R is inside to outside. Inside to outside function, starting theta counterclockwise to final theta. What is dA? So the order is R and then theta, but what is dA? So I got a picture here. So let's fill in things. So this is just a little tiny element, but it's blown up, right? So if this is a really small element, then we have a little small change there and a little small change there. So let's label everything. This then is our theta. So then this would be what? D theta, right? This is our R. From here out, how far away we are from the pole. And then, so this is dr. So is this arc length right there d theta? Because we're really still going to kind of do the area of a rectangle to get dA. So it's going to be that, whatever that question mark is, times dr. It's going to give us a rectangular area there. Is it d theta? Is that what that length is right there? It can't be, because it would be different depending on r, right? That's going to increase. It keeps getting that arc length right there, or that dimension, keeps increasing as r increases. So it's not d theta. So what is it? So we have to go back to, if you have on a circle, for say an angle called alpha and radius r, what is the arc length? What is the arc length of part of a circle with radius r swept through angle theta, or alpha?
Yeah, right? So it's r times alpha. Did any else of you know that?
Could we also think of it as just like a central angle and then scaling it up by a factor of r? Like if the radius were 1, you would have alpha and alpha.
Mm-hmm.
And then we just scale.
Well, it goes back to this goes back to the definition of what an angle measure is.
Right, theta is s over r. That's good.
So therefore, what is this? What is that dimension then? So this dimension right here would be what, according to what we said in general about circular arcs?
Would be the inner r times theta,
And what is theta?
or d theta in this case.
Yeah. So that dimension is r d theta. Therefore, dA is dr times r d theta, not just dr d theta, because d theta is not a length, right? D theta is a change in angle measure or openness. It's not a length. To get length, you need to multiply by the radius, and then that gives you the length. So now that little rectangular area is dr times r d theta. And so our polar double integral then is complete at, so we go h1 theta, so r1 to r2, theta 1 to theta 2. So dA is not dr d theta, but r dr d theta. Because d theta is not a distance dimension. R d theta is. So what happens to the r? What happens to the r? Well, it's part of the dA, yes. But now this is we know this is all multiplication, right? This is our integral is, remember, by rate of change. It's rate of change times little change in independent. So this is multiplication. So then the r attaches with, in terms of solving the double integral, the r attaches with a function and gets multiplied over here. Okay? So it comes to the party with dA, but it leaves the party with f. So what we need practice in is these regions, defining the, in terms of the regions, our two-dimensional regions. We need practice with, given a two-dimensional region, defining the limits of integration. What's the starting r, final r, starting theta, final theta? And then we'll set up double integrals, and then solving them is just the same, but you just have different variables now, r and theta, rather than x and y. Okay, any questions on our polar double integral? Okay. Can I erase? Okay, so he's got some practice problems here. So I don't care about what the function that we're integrating is, right? So how does the function that we're integrating relate to pictures like this, right? This is the horizontal plane. Like this is our, like we're superimposing polar coordinates on the xy plane. So the function that we're integrating, right? We do double integral of f. How's that relate to this, what you're looking at here? So double integral f. dA. So what we're looking at here, how does f relate to what we're looking at in these pictures? What's that?
That's for the function in 3D, this is just the region boundary.
Okay, so that's for the function in 3D, and this is just for the region. So this, you imagine these regions are in the horizontal plane. Something like this. Okay, and then we have a function that's separate from that, and that's what we're accumulating, or that's the function that we're integrating. And so that's a surface in R3, right? That's a surface in R3. So what we're working on now is just the regions, we often call that D, right? Like D for region. And so we're just working on setting up the limits of integration, right? So that's just the establishing what all the points of D that we're going to consider for the function f, right? In terms of integrating f. Okay, so I'll take attendance, and you guys are figuring out what are the limits of integration for each of these. So R1 to R2, theta 1 to theta 2. So 4 different problems there. Is the task clear? So you're either making progress or you're getting help. If you're lost, just talk to someone around you.
I used to assume this was like 5.
Okay, so we'll do the first one together. So for a given theta, R goes from what to what to get the points in the region? 0 to 2. And then we take all of those, like all of these like radial strips, right? These radial strips from what angle to what angle? 0 to, so 0, here's the starting angle, right? Starting angle 0, all the way to 5 pi over 4. So that would be the limits for this first one. Then we'd have f times r d theta. Does that make sense? So for a fixed angle, to get all the points in that region, in this case, you'll start at r equals 0 out to r equals 2. And then we'll take each of those from theta equals 0 around to 5 pi over 4. Following it? Yeah.
Did you just guess that it was 45 degrees in that quadrant, or did you observe
It's going through this point right here. Yeah. So it's
Slices the square along the
it's going in that point right there.
Oh, I see that, yeah.
Yeah. And so that's just going right through these like this.
That makes sense.
So does this.
Yeah.
But yeah, you would have to guess. I'm not giving you any. The only information you have is a sketch. So you're guessing, you're eyeballing it.
But can't you be convinced since the line goes through the diagonal of one of those unit squares?
Yeah, but that's still a guess. That's still.
Good guess.
Okay, so you want to work on the other three? Okay, let's talk after class.
Yeah, sorry.
Yeah. Are you done?
Yeah.
Anyone still working on them, or are we mostly done? Are you done? Most are done. Okay, so this one is R goes from 1 to 3, then pi over 2 to pi. And then the same thing, right? F, R d theta. Okay, this one, R goes from 0 to 2 again. Angle goes from pi to 7 pi over 4. Same thing, F, R d theta. Please.
Can you do the negative? Like, can I do like negative pi pi over 4 for that last one?
Yes, but when we get into these polar integrals in R3, they don't do negative angles. It's not like, so yeah, so when you introduce polar coordinates, you have the freedom of negative positive angles and negative r's and positive r's, but we kind of restrict, now we're talking about like polar coordinates in R3, they kind of restrict the domains. They say let r be positive, let theta be positive. So, but yeah, you're right. So this is the same as negative pi over 4 to negative pi. But they don't really use it. They stick to positive r values, positive theta values. So for this last one, r goes from 2 to 3, theta. So here we're kind of stuck, right? We got to do something with negatives, right? So this would have to be negative pi over 4. After I just got done saying that you don't. You have to here, right? So there's no way around it.
You have to have something to do with negative angles.
Why can't you just use
Or you could do what? 7 pi over 4 to whatever that is. 9, 11 pi over 4? Yeah. So the other possibility would be 7 pi over 4 to 11 pi over 4. Any questions? Yes, please. Yeah, I'm trying to think about. Yeah, it's fine because everything's constant. If you actually had functions here that were like radius as a function of theta that actually wasn't constant radii, then it would be important that your angles are in the right. The answer to the question is yes, because we've got constant radii, right? Because we got constant radii, and we're doing constants for the thetas. You're okay with that. Okay, other questions? Okay, so example. So here is a double integral. First, I want you to sketch the region in the xy plane. Then I want you to change the order to dx dy. And then I want you to change the integral into polar coordinates. And then we're going to solve the integral. We've got 8 minutes. Okay? So we don't want to get bogged down on the sketch and part 2, but we do want to do those, but we want to make sure we have enough time to get to the polar coordinates. So try to work efficiently. Remember, these are geometry problems. Whenever you're changing the limits, you're making a sketch first, get a good sketch, and then you're scrapping the old limits, and you're writing the new integral based on your sketch. Remember that? So you don't want to kind of try to do trickery on like changing around the limits to get the new limits. The new limits you're going to get from your sketch, right? From a good sketch, like you're starting over, okay? Okay.
So when we're changing the order, we're going to go from what to what here? From left to right, and then bottom to top. So left side would be? Negative square root of 16 minus y squared. To right would be? Left to right would be, now the right is 0. See that? And then we're going to add up all of those, starting at up until positive 4. Negative 4 to positive 4. Notice I made those new limits based on the picture. I wasn't looking at the old limits. I made a good picture, and then based on my picture, I created the new limits. Okay, and so our function's the same. But now we're at dx dy. Questions on the sketch or number 2? Type 2, double integral. Does it make sense? Okay, now we're going to switch it to polar. So now you're well practiced at writing the limits. What will the limits be? Just like the previous examples? 0 to 4? And? Pi over 2 to 3 pi over 2, just like the previous slide. All those practice problems we did. So starting at the full all the way out to 4, and then from pi over 2 to 3 pi over 2. Okay, now we got to rewrite the integral. X is r cosine theta is x. The square root of x squared plus y squared. It's just r, right? That's the hypotenuse. Or it's the square root of r squared. Either way, you still get r. And then what's dy dx? R dr d theta, right? Not just dr d theta. Dy dx is like dA, and then we know our dA is r dr d theta. So what does that become here? Pi over 2 to 3 pi over 2. So these go, right? R and R's go. So now, the given integral, this double integral, and this double integral all have the exact same value. They have the same value. They're just different ways of expressing the same thing. So, if you have to find that value, what are you going to do? What are you going to use? You want to integrate x over square root of x squared plus y squared? Okay, so with respect to x, it's actually not that bad because you've got, this is like a u substitution or undoing the chain rule. Not too bad, but it's still complicated compared to this. So your easiest road to finding the value is definitely the polar integral. And why? That's because the region itself is the most suited to polar integration, polar coordinates, because it's based on the circle centered at the origin. So this would be the most efficient way to find the value of the given double integral. Okay, really important example. There's lots of good stuff in there. Any questions before we dismiss?